Yes, good afternoon.
Hello,
You can start. Yes,
welcome everyone. Thank you for joining us for today's seminar. Good afternoon to all. Myself, Haji Rubia, working as the assistant professor at ASPM K.T. Patil College of Pharmacy, Dharashiv. I would like to take this opportunity to host this event and to welcome you all participants in second session of one-day national seminar on applications of QBD in pre-formulation study. Hope you all enjoyed the last session conducted by Dr. Mahapade sir. Now, for the second session, we have a very dynamic personality with all of us. So, I'd like to give a warmest welcome on a behalf of Adarsh Institute to Dr. Degan Mohammad Hassan, Professor and Principal, YB Chavan College of Pharmacy, Chhatrapati Sambhajinagar. Welcome, sir. Dr. Degan sir has completed schooling from Bishop's School of Higher Secondary Education from Ferguson's College, Pune. He is an alumni of Pune College of Pharmacy. He secured distinction in B Pharmacy and ranked first gold medalist in M.Pharm Pharmaceutics. He was awarded PhD in Pharmacy by University of Pune. Dr. Degan sir has 29 years of teaching and research experience and 9 years of administrative experience as a principal of YB Chavan College of Pharmacy. He has guided more than 95 M.Pharm students for their dissertation in subject of pharmaceutics and quality assurance, and 9 students have completed their doctoral study under his guidance. Dr. Degansar has Indian patent granted and 6 patent application published. He has co-authored one book, more than 104 research papers in peer-reviewed national and international research journals. He is a MOEIIC Innovation Ambassador and has been convener, speaker, session chairman, co-chairman at various seminars and national and international conferences. He is a paper setter, examiner, member of staff selection, inspection committee, board of study, assessor of various universities and statutory bodies such as PCI and NAC. Dr. Vegansar is a member of International Society of Pharmaceutical Engineering, Florida, USA, life member of Indian Society for Technical Education, Indian Pharmaceutical Association, Association of Pharmaceutical Teachers of India, and Association of Community Pharmacists of India. He was the Vice President of Association of Pharmaceutical Teachers of India, Maharashtra State from 2013 to 2016. Dr. Degansar has awarded by various awards such as E4E Academic Leader Award 2010, also Shikshan Seva Gaurav Puraskar on 3rd January 2015, also 11th Innovative Education Leadership Award Mumbai on 16 February 2019, also 27th Business School Affair and Devang Mehta National Education Award for the Best Professor in Pharmaceutics awarded on 29th August 2019 at Gnata Chhatrapati Sambhajinagar. So there is a lot more to tell about the sir. So we have such an eminent personality today. So I heartily welcome you, sir.
thank you.
So before starting the seminar, I would like to request all the participants, if you have any questions during the presentation, please type them into the chat box in your control panel. We will have time for question at the end. Now I would like to request Dr. Degan sir to start the session. Please, sir. Over to you, sir.
Thank you. Thank you so much for your kind introduction. And at the beginning, I'd like to thank the management of KT Patil College of Pharmacy, the principal Amol Joshi, Mr. Dr. Amir Kazi, and all the faculty members there for inviting me for this seminar. So, since already there has been a seminar on a similar topic in the morning session by my dear friend Dr. Ma Parle sir, I would continue with the same topic but with from a different point of view. So, basically, uh, we are dealing with pharmaceutical product development, and what I'm going to focus on is the use of design of experiments in optimization. So let's first understand what optimization is all about. The term optimization is defined as to make perfect, effective or functional as possible. Why optimization is necessary? Because optimization provides us a scientific approach which helps us to improve, innovate with reduced error and making the process reproducible with a reduced cost, making it more efficient, and also helps us to save time. So, optimization is basically improvement. So, what we see today, uh, any particular product, even take the example of your mobile phones, what is there today will not be the same tomorrow. Tomorrow, you'll be having a more effective and a better mobile phone, and you will be wanting that. Similarly, any product, whether it's a pharmaceutical product or a pharmaceutical process, we would always want to have the best. What is best today doesn't remain best tomorrow. We need to keep on improving, and that particular process of improvement to make it more perfect, your process or your product, to make it more effective, to make it more functional, is nothing but optimization. So there are various optimization parameters. All of us are aware of these parameters. First and most importantly is the problem type. When you want to optimize any formulation or process, you should understand that there are two problem types. One, the problem is a constrained problem, or it could be an unconstrained problem. Most of the pharmaceutical problems are constrained problems. Constrained problems means they are within some limits. It is not an open problem. It's not like, somebody telling you make the hardest tablet. That would be unconstrained. But usually, when a problem is given to you in pharmaceuticals, it is like make the hardest tablet, but it should have a disintegration time within 20 minutes, or it should have a dissolution time that 50% of the drug should dissolve, say, in 30 minutes or in 15 minutes. So these are some constraints that are put into that particular problem, and thus most of the pharmaceutical problems are constraint problems. Similarly, in pharmaceuticals, we consider two types of variables. One is an independent variable. The variable is such that you can make changes. It is independent. It is up to you to make the changes. These variables can also again be product variables, or they could be process variables. Independent variables, say for example, in uh, producing the best tablet would be making variables with regard to its diluent ratio, or with regard to its compressional forces, this being a process parameter, or with regard to the disintegrant level, binder levels, lubricant levels. These are all independent variables. And once you make these changes in the independent variable, you would want to know that how these changes are going to actually affect the responses or the dependent variables. So the dependent variables could be n number of dependent variables. For example, for a tablet, you could have disintegration time as a dependent variable, hardness, dissolution, friability, weight uniformity, content uniformity, and so on and so forth. Okay, so these dependent variables are dependent on the independent variables, on the changes that you have made. The independent variables are denoted by X, whereas the independent variables are denoted by Y. Okay, now there are various optimization methods which you have already studied. I'm just giving you a brief idea so that we actually could use this for a particular problem that we would be solving at the end of the presentation. So optimization methods could be a classical optimization method, wherein what you basically would be doing is you will be setting up a relationship between the dependent variable, that is the response, and the independent variable, which is also known as the factor. So you would be having a relationship that would be y corresponding to fx. Now, in a classical optimization method, you could have a mathematical relationship like the one I just told you, y as a function of x, or y as a function of x1, x2, depending on the number of independent variables. Or you could also present it in a graphical form, that would be maybe in a form of an response surface graph, or a response surface plot, or also known as the response surface methodology, RSM, which Ma Pandey sir today in the morning session explained to you. Or it could be represented in a simple graphical representation if you have a single independent variable. If you have two or more independent variables, then it could be in a form of a 3D plot. Okay, if you have two independent variables and you want to seek the effect of those two independent variables on the dependent variables, then you could represent it in the form of a contour. So that was the classical method. Now, the method that we would be more focusing on is the statistical design or the statistical method. In a statistical method, there are two techniques for operating these methods. One is known as the real-time technique, in which you have some input data. Say, for example, your independent variables, you are making changes, you are running that at real time, and then you're seeing the output. That means you are seeing the responses. So this is a real-time method that you would be making changes as and when you are operating these independent variables real time. Okay, and then checking out the responses. So these changes would be made incrementally to see to it that how these changes are going to affect your formulation or your process. Say, for example, you want to optimize the sterilization cycle. You are making incremental changes, say, for example, in the pressure of the autoclave that you are using, and you are optimizing the best pressure that would be required for this kind of moist sterilization technique. Okay, or you would be making or checking out the change in the temperature with respect to the change in the pressure. This is being done real time, and thus it is being optimized to give you the best or the most optimum sterilization cycle. Say, for example, such an operation is known as an evolutionary operation or a EVOP method or an evolutionary operational method. Similar techniques known as simplex methods are also available, wherein you would be making changes in one factor at a time and checking out how these changes are going to affect the simplex. Simplex means a form. So this is known as a real-time technique. Other techniques, statistical techniques, are available, which are based on data which has been obtained already on real time. And these data are used to set up a mathematical relationship. And then the optimization is done using this data. And then again, finally, you run it real time. So these are some techniques which you could use for your optimization, a classical method or a statistical method. I'll leave at that and let's go to the scope of experimental designs, because finally what we are going to do is we are going to use these experimental designs for optimization. So what are experimental designs and why experimental designs are so important? You should remember, for designing any experimental strategy, before you start any experiment, when you're designing a strategy, how to do that particular experiment, how to do that particular research, how to go about optimizing a particular product or a process, for that you have to lay down some strategy. For that strategy, there are some things which are essentially required. The first thing which is essentially required is expertise and experience. So we find most of the PhD students have their guides, the M Pharmacy students have their guides. Why? Because these guides are experts in their field. They have got the requisite experience so that they can help you out. Okay. So many times the researcher needs to have these kinds of expertise and experience, which is essential for him to set up the experimental strategy. Then you have to define the measured responses. What kind of responses you want? Responses means the dependent variables. So what kind of responses you are seeking, you should define those responses. Say, for example, if I'm formulating a tablet, I've already told you the kind of responses I would want to have. Okay, then you identify the factors. Identifying factors means identifying the independent variables. So you should be in a position to identify which independent variables you should be using, which are those active independent variables. So identifying the active independent variables actually done during the screening method. Okay, then select at least 2 to 7 factors for the treatments for these experiments. So out of so many factors, so many independent variables, you would be selecting few of them which would be essential to have, so that you could study their impact on these responses. So how to identify that would be done during the screening methods. Then depending on the qualitative and quantitative factors that you select, you would be selecting their levels or their values. Most of the time the quantitative factors are given numerical values, and these numerical values, which are known as natural values, are converted into coded values for their application. Then finally, you have to select the design, which is the most important stage. So that design is the experimental design that you would be selecting. What is a how experimental design can be defined? It is a strategy for setting up experiments in such a manner that the information required is obtained as an efficient and as precisely as possible. So remember, our optimization is techniques are basically based on saving time, saving resources, and thus saving money. So this is to be kept in mind when you are framing an experimental design. So what is the basic purpose of the statistical design? The basic purpose of a statistical design is basically to set up a relationship or to determine the relationship between the factors and the responses. So that is the basic utility of an experimental design. So let us see what are the various types of experimental design. So it's not that this is something new. From time immemorial, when research actually was started, whether it was due to serendipity or whether it was due to some scientific means of research, there was always some kind of experiments that were performed. So it is really very useful for screening the variables, your experiment and experimental design. And it actually has an impact on the drug product and also the final responses. These final responses, you could relate it to the critical quality attributes that Ma Parle sir taught you in the morning session. So our response, the dependent variables, nothing but the CQAs, critical quality attributes. Okay. And whatever variables we would be doing is we'll be making changes in the material attributes. And if it's a formulation, if it's a process, we'll be making changes in the process parameters. So sir must have told you about the CPP, that is critical process parameters. So that's what we would be actually doing using the experimental design. So what kind of designs are available? The basic design is a success failure design. So what is a success failure design? What you term it as trial and error design. So you have one run, you have no factors which are varied actually, and just you see the outcome. So you take a particular, say, if take the same example of a tablet, if you take a particular concentration of a particular diluent, okay, then a particular concentration or amount of your binding agent, a particular concentration or an amount of the active ingredient, a particular concentration or amount, say, for example, of your diluent, your lubricant, and then you prepare a tablet and see what are its effects. And then again, you change the concentration, again, prepare another tablet, see its effects. So, what you're doing actually, it is a very you're going for a trial and error method and just checking out whether this formulation is going to give you the desired result, yes, or it is not giving you the result, that is no. So it's a easy design, it is easy to analyze, but it lacks any comparison and it is really inefficient and it very time consuming also. So rather than that, you can go for a OFAC technique, that is one factor at a time. We talked about the evolutionary operations where we could make changes, incremental changes, and particular one factor, and we could check out how it's going to affect a particular response. Okay, so similarly here, you could have several runs in which one factor is varied, and then you could have two outcomes where that factor was varied and where the factor originally was used. Say, for example, you could have a method known as the presence absence model. Okay, or you could have a method known as the reference model. So initially you had that, say, for example, you use a lubricant that was talc, and in the next formulation, you omitted talc and you used magnesium stearate. And now you want to see the flow property. Okay. So you are seeing the results, your outcomes of magnesium stearate in reference to the one that you had already used, and that was talc. So your variables are two different qualitative substances. So these are qualitative variables or qualitative factors that you have varied. And you have checked out a particular outcome, say, for example, angle of repose, or another outcome, say, Hausner's ratio, or another outcome, Carr's index. So you could do that. So what you're doing, you are varying one single factor, that is one factor at a time. Now this is also okay, but this is not sufficient to actually give us the idea about the interaction of various factors or various independent variables on our responses. For that, we need to have a better technique. And this better technique is available if you use what is known as the experimental design. Okay, so that means if you could vary many factors, okay, and see the effect of varying these factors on your responses. One such example is cited here, that is factor in an experiment of extrusion speronization. So in this, you can see the factors. There are process factors as well as there are formulation factors, and you can see we have varied these factors at two levels. One is known as the lower level and the other is known as the upper limit or the upper level. Okay, so you can see we are varying all the factors. Percent of binder is being varied, amount of water is being varied, granulation time, spheronization load, spheronization speed, extruder speed, spheronization time. All these are being varied at two levels. After varying them, we prepare a particular matrix and we run these experiments and see the results, say, for example, on particle size, or we are seeing the results, say, for example, on the shape of these particles after after extrusion and spheronization. So you can see here, I've got 8 runs for these various variables or factors: binder, water, granulation time, spheronization load, spheronization speed, extruder speed, spheronization time at two levels. So I've prepared this matrix. You can see each and every run, each and every experiment that I'm going to perform is having different permutations and combinations. Okay, so this is what is known as the experimental plan. Okay, so you could run multiple runs for multiple changes that you have made in the factors at multiple levels. Here the levels are 2 level changes. You could have 3 level changes, and so on and so forth. And you could have your own experimental design. But whatever design you're going to prepare, it should be scientific. It should have a particular structure. So a design of experiment is nothing but a structured, organized method for determining the relationship between the factors affecting a process and the response of that process. What is the advantage of this design of experiment? You can have multiple runs, multiple experiments. You can have multiple factors which can be varied at time. You could have multiple outcomes. You can have various dependent variables studied, multiple outcomes. And you could also find out the interaction between these factors. When you vary the factors, what actually happens to the outcome. So that kind of interaction can also be seen, and it is much more efficient. Okay, and what is most importantly, you could use this for optimization. Not only for optimization, you could also use it for enabling to create what is known as a design space. Okay, to create a design space. So design of experiments, the strategy would be different depending basically on the kind of experiment that you are performing. But for a design of experiment, there are various stages that needs to be considered. The first stage is you should describe your problem. So I told you most of the pharmaceutical products or processes, they are constrained. So your problem would always be constrained. So you should describe the constraints. You should describe your problem. What is your problem? What you want to actually experiment on? Whether you want to increase the dissolution time of your tablet, you want to make an IR tablet, instant release tablet, or whether you want to go for a sustained release tablet. What is your problem? What kind of a dissolution profile you want? Okay, what do you think should be the tablet integrity? What should be its hardness? What should be its friability? So you should describe the problem. Then you have to analyze existing data. As I told you, in the statistical method, there are two techniques. One is real-time data, the other is data which is already available. So you should analyze the existing data which is there for a similar type of a problem. Then you have to identify the situation. What is the data that is there? What is the kind of experiment that you would be wanting to actually run, and uh, what kind of outcomes you desire. So then you have to identify that situation. Accordingly, you have to list down the factors. So there'll be various factors, process factors, there'll be the formulation factors that you will have to list down. and you have to see to it that these have been definitely listed down, and then later on these have to be screened, okay, so as to identify the active factors. So then you list the experimental responses, okay, create a mathematical model, define the constraints and the limits, and then finally prepare an experimental design or a matrix, then an experimental plan, and then go for the experimentation, analyze the data, and then you can have your conclusion, and then you can go for the next stage, depending on the stage at which you are doing your experiments, whether the stage is at the screening stage, whether you are studying the factor influences on your responses, or whether you're going finally for the optimization. So depending on that, you could actually go for the next stage. Okay, so the selection of the design and the methods would again depend on the kind of experiment and at what stage you're performing the experiment. If you're performing the experiment at the screening level, then there you will have to go for the different kind of design, because at screening level there are many factors. So usually the designs that you use here are fractional factorial designs. Say for example a placket Berman design, we'll see an example of the same later on. So we could go for a fractional factorial design, or you could go for a d-optimal design, which is based on computer algorithms, because in screening there are many factors and you have to identify the active factor, the factor which is going to actually have the influence on your response. Then next is the factor influence studies. Next, you could be going for predicting the response within the experimental domain, which is known as the RSM, or you would want to go for optimization, or you would want to go for process and formulation validation, or finally, quality of the product and the process. So all these are the various types of stages that you would be performing, and accordingly you would be using various kinds of design. You cannot use the same design for optimization, the one you have used for screening, obviously, because here in optimization your number of factors are very limited. You have come down to the most active factors, so your optimization design would be different in comparison to the screening design. Okay, now there are some terminologies which you should be aware of. I know most of you are already aware of these terminologies, but since we are in a flow, let's understand that the factors are of two types. One is a quantitative factors. Quantitative factors are factors which are having some continuity. So this is the factor space, and within the factor space, there is continuity for the quantitative factor. Okay, so you can identify the quantitative factors. You can see X1 and X2 are given here at three different levels. The uh, coded levels are -1, 0, +1. Here again, -1, 0, +1. So this is basically for the volume, and this is basically for the time. So you can see here that the any point within this space, which is known as the factor space, if I put this particular point, you can actually define the point because there is a continuity. It's a quantitative factor. So this point would be, say, for example, 12 minutes. This point would be, say, for example, 2.5, 12 liters, and this would be around 2.5 minutes. So I can identify these points. But if it's a qualitative factor, say for example, here qualitative factor for a mixer granulator, on one side I have the diluents, on the other side I have the three different machines. So you can see here again the limits that I put here are three limits that I've set, or three levels that I've set over here. So these levels are qualitative levels. So there is no continuity. If I put this particular point, you cannot define which diluent or which machine. So qualitative factors are discrete factors. So these are some of the factors which I need to identify at the screening level itself. कौन सा machine मैंने use करना, which machine I should use, which diluent I should use, whether I should go for lactose, whether I should go for cellulose, or whether I should go for mannitol or diphosphate, which particular diluent I should use, that I should be identifying the screening level. So these are some of the qualitative factors. One thing very important, that the factor space here is having discrete points and there is no continuity. So that I should remember later on when I'm going for my optimization or my screening studies. Anyway, usually we set up a mathematical model. The mathematical model is set using coded variables. Okay, so as I told you, there are natural variables. Machine A, B, C is the natural variable. The coded variable would be, say, for example, if I have the this as x1, so it will be x1 A, B, C. Okay. Similarly, x2, I will be having x2 1, that would be lactose, cellulose, mannitol, and phosphate. 1, 2, 3, 4, like that. Okay, so these are the coded variables for the actual variable. Accordingly, I can have a mathematical model setup. So mathematical model would be in a polynomial form. Y is equal to beta 0 plus beta 1 x1, beta 2 x2, beta 1, say for example x1 square, beta 2 x2 square, beta 1 2 x1 x2, and so on and so forth. So there will be a polynomial setup. This is for a second order model having two factors, x1 and x2. So this is the polynomial. What is the importance of these beta values? Beta values are actually the constant values which are giving you the magnitude of the effect. So magnitude of the effect with regard to x1 and x2, these two factors on y. Y is the response. तो इसका कितना इफेक्ट रहेगा, उसका मैग्नीट्यूड दैट इज बीइंग गिवन by the beta values. Beta value, say for example, beta 1 x1 is the magnitude of the effect of x1 on the response y. Similarly, beta 2 x2. Beta 2 is the magnitude of the effect of x2 on y. So these are very important. The coefficients are very important here in such a mathematical model. It will help us to understand the relationship not only between the response and the various factors, but between the each factor and its effect on the response. So this is what is the essence of the mathematical model. So there can be various experimental designs that you could be using for screening. As I told you, most of the screening designs are for identifying the active factor, the factor which is actually going to have an influence on the response. उसको identify करना हमने, बहुत सारे factors है, process factors है, फॉर्मुलेशन फैक्टर्स है, फैक्टर्स मतलब इंडिपेंडेंट वेरिएबल्स, बहुत सारे हैं, बहुत सारे लेवल्स है, तो उसमें कौन सा एक्चुअली इफेक्ट कर रहा है उसको हमको यूज करना है. दैट आई वांट टू शॉर्टलिस्ट एंड दैट्स व्हाट आई एम गोइंग टू यूज इट लेटर on during the optimization process. So the screening is screening out the inactive factors. This is known as the sparsity effect. Screening out the inactive factors and selecting only the active factors. Okay, this is what screening is all about. For screening, as I told you, you usually use a fractional factorial design. You don't use a full factorial design. Okay, then you'll have many experimental runs. You cannot afford that. So you want to minimize the experimental run. So you will be using a fractional factorial design. Most commonly used in pharmaceuticals is for pharmaceutical products is Plackett and Berman design, which is also a fractional factorial design, also known as the Hadamard design, and computer algorithm kind of a design using computer algorithm is known as the d-optimal design. So this is these are the two most commonly, but there are so many other designs that you could yourself also frame. It could be symmetric or it could be asymmetric fraction factorial design. So that is for screening. Once you have screened, now you want to optimize. Now you want to make the best formulation, by making changes in the factors which are going to have the greatest influence on the responses that you desire to optimize. Okay, so for that you would be using various optimization techniques. So these are some of the optimization techniques I have mentioned here, but there are many other applied optimization methods which can also be used. The first two methods I explained to you while we were discussing the statistical design. Okay, that is the evolutionary operation where you are making small incremental changes to improve the particular response. Okay, and the other is the simplex method where you are using the form, which is nothing but the simplex. Simplex is just a geometric figure or a geometric form which is being used to optimize a particular process. Here the optimization is being done for to generate the highest absorption by making changes in the flow of two reagents. Okay, so this is one particular technique that can be used. It can also be used for optimizing various say for example capsule formulations, or for direct compression for tablets, or for even liquid system for optimizing the physical stability and so on. There are various simplexes which are available in literature. You have the downhill simplex, also you have the Nelder uh, um, Mead method, or Nelder Mead simplex method, which is available. Okay, anyway, so coming to the full factorial design. So after you have done your screening, you could go for a full factorial design. What is a full factorial design? In a full factorial design, what you would be actually doing is you would be making the permutations and combinations related to the number of factors at the number of levels that have been defined. So you can see in this particular run, I've got three factors, x1, x2, x3, and I've defined two levels. So 3 into 3. So I would be having 9 runs. So I could have 9 runs for a full factorial design using three factors at two levels. Okay. Now, these designs are very important because we can use these designs, actually a full factorial design, for the final optimization of a formulation and also generate polynomial mathematical interaction expressions. So this is an example of polynomial mathematical interaction expression that can be generated again in a polynomial equation form that I explained during the mathematical model. Y is equal to beta o plus beta 1 x1, where y is the response, which Ma Parle sir told you in the morning. It is the critical quality attribute, say for example, or it could be a critical process parameter. Okay, so that is your response, and your x is basically your CMA that you would be identifying, that is the critical material attributes. Okay, it could be the critical material attribute, so that could be your x values. So x values, say for example in this particular case, your x values is cornstarch, which is you being used as a binder, and stearic acid, which is being used as a lubricant. Okay, so these are x1 and x2 values, and you could have this kind of a response. Then you have to define the constraints. As I told you, the pharmaceutical problem is always a constraint problem. So you will be defining the constraint. Okay. So the constraint would be defined depending on the kind of responses you want to seek. Say, for example, here the constraints have been defined for hardness, constraint is defined for in vitro release, and for friability, as well as you can see the constraint is being defined for the tablet volume. So you will be defining the constraints, and accordingly you will be running the experiments. So once you run the experiments, since here you could see you have got two factors at these two levels, x1 and x2. You could have three factors, but here since we are running two factors here, these are the kind of contours that I would be obtaining. So you can see here I have obtained a contour for running stearic acid. Okay, which is one of the factors, along with your cornstarch. And this is the kind of contour I've obtained with regard to the percent dissolution as well as with regard to the hardness. Now, since I've already defined the constraints, I could superimpose these contours and I could define what is known as the factor space. Okay, I could be defining the factor space. Okay, so this factor space is very essential because this factor space would actually be giving me the idea of what is known as the design space. So already Ma Parle sir in the morning session has told you about the ICH 8 guidelines, which gives us the opportunity for avoiding SUPAC. Okay, that is scale up and post approval changes approvals. So we can avoid that if you could define a design space. So if I can define the design space, I could avoid again going back to the regulator to seek approval if I'm making some changes within this design space. Okay, so the design space is actually the central point, or it is this particular area. Okay, so this is the area, this is the design space. And then within this design space, I could have a most optimum point, which I would be using for my pivotal formulation. Okay, so this is the optimum point within the design space. Then I have a region of interest. The region of interest is this particular area. Why this is known as the region of interest? Because this is the region wherein I have laid down the constraints. So, for example, I laid down the constraint for hardness between two levels, and I laid down the constraints for dissolution between two levels, and I superimpose these two levels to get this particular design space. So this will be the design space. This area will be what is known as the region of interest. And then I would have this area, which will be the region of operability. This whole area will be the region of operability, where I've done the operation, where I've actually run the various experimental runs and noted down the various factor values. Okay, that is x1, x2. Uh, I've run and I've seen the y values. Okay, hardness and percent dissolution share. So that was be the region of operability. And then I have the uncertain space. Uncertain space is beyond this particular graphical representation, which is the uncertain space. So anything beyond the design space, that is beyond the operational space, is known as an innovation, and for which you have to again get approval from the regulator. You have to go for approval after making SUPAC. Okay. Okay. So this was one kind of three kinds of designs that we saw for basically for optimization. One is the evolutionary operation, which is a real time, simplex, which is another real time. Then I could have the Lagrangian method, which is the full factorial design. And then I could be actually using what is known as the box Bacon design. So we can go for a box Bacon design and have similar relationship. That means I would be having a relationship using a quadratic model and an equation, which is given here. And I could also go for the Box Wilson central composite design, which is a very common design, which is nowadays used for optimization. Similarly, I could use computer search methods for optimization, canonical analytical methods for optimization. And now, most recently, artificial intelligence is being used, and what is known as the artificial neural network, which is being used in optimization of pharmaceutical formulation. This artificial neural network is basically based on RBFN, which is the radial basis functional network. This is comprising of multiple inputs, and then there would be what is known as the hidden layer giving you the desired output. Okay, so this is the artificial neural networking that could be used for optimization, for obtaining a relationship between the various factors and the particular response that you are seeking. Factors would be your inputs, and the response would be your final output. Okay, so this is by using the recent artificial neural networking systems, or the ANN systems. Anyway, I would now want you to go ahead. I would now want to go ahead to give you an example of this particular techniques which have been used uh, with the QBD approach, which was explained to you earlier by Ma Pallisar, for optimization of a formulation. So this is for the development of a nasal spray using the design of experiment as a tool for quality by design approach. Okay. So I'd like to just give you an example of a similar kind of study that has been done by one of our students. So first we should understand that why we would be going for any such particular experimental design. Here this student has gone for an experimental design because he wants to make some submissions. And this submission that he's trying to make is an ANDA submission, abbreviated new drug application submission that you want to make. So yes, you know now since 2013 onwards, it has been made mandatory that for all ANDA submissions, we should be using what is known as the quality by design technique, which Sir has explained very well in his earlier lecture. That is the ICH Q8 and Q9 and Q10. So he has explained that, and based on this, product development is being done now in the pharma companies. So what they are basically doing is they are basically trying to develop a generic drug which is already available in the market. So they would also get a piece of the cake of the market in terms of the commercial value of that particular product, which is already available in the market. It's already in the market because it has already been launched by the innovator. so which is known as the RLD product. So it's already there. Reference listed drug product is already there in the market. And now, once the patent has expired, and now I have an opportunity to again also market my product in the same market, say for example in the US market. So I would have to seek the AND approval. To seek the AND approval, I need to basically present my product in a very scientific manner and to prove that my product is similar to the product which is already available in the market. For that, QBD approach is something which is now sought by the regulator. Okay. So there is an FDA review which focuses on the characterization of the reference product and the materials, the design of the product and the process, the pivotal bio batch, that is the batch that you had prepared for which you have already done some bioequivalent studies, the bioequivalent studies that you have done to show that your product is having a similar plasma drug concentration time profile like that of the RLD, that is a reference listed drug, and then finally the commercial product manufacturing. So the FDA would be focusing on that, and I would have to use some tool to see to it that I include all these parameters uh, as far as the understanding of my product so that it is approved by the FDA authorities. Okay, so I need to formulate or develop my products. So to formulate or develop any particular product, you should have what is known as the formulation strategy, and you should be following that formulation strategy. So to follow the formulation strategy, first and foremost, you should select the route of administration of your drug. Since my drug product was a nasal spray, the route of administration obviously was intranasal. Then I have to select the target dose. So the target dose for flunisolide was 25 micrograms per spray. Then the dosage form, whether it's going to be in the form of a solution or whether it's going to be in the form of an emulsion, all this will be depending on the physiochemical properties of the drug. This dosage form selected here was the solution type nasal spray. Remember, I'm filing an ANDA. Already there is an RLD product which is existing in the market. I'm trying to make a similar product to what which is already existing in the market whose patent has expired. Okay, and I'm just trying to show you how I can use QBD techniques and design of experiments to do the same, to prepare the dossier for my product for submissions to the regulator. Okay, so yeah, next strategy would be the desired delivery profile. Okay, so where it would be localized in the nasal cavity, say for example, whether it would be, in the respiratory region or whether it would be in higher region, so that I need to actually identify for my product. Then the API characterization, whether the API is water soluble or whether it is water insoluble. Then the percent of API drug load in the dosage form, how much percent I would want to go for the API drug load. So you can see here, I've already defined all these factors over here. So I've done a thorough study of the RLD and I've defined these factors, and thus I would be using this formulation strategy accordingly. Okay, then what are the steps that I would have to follow? So these are some of the steps that already Mapale sir explained to you in the morning. I'm just repeating. So the first one is analyze the reference listed drug. जो प्रोडक्ट ऑलरेडी मार्केट में अवेलेबल है, जो इनोवेटर प्रोडक्ट ऑलरेडी मार्केट में अवेलेबल है, RLD प्रोडक्ट, उसको एनालाइज करो. Analyze it means to chalk out or write down or define the quality target product profile. Okay, so I have to prepare a QTPP for the product which is already available in the market, the RLD product, and then I have to define what is known as the critical quality attributes. That means I have to define the dependent variables, I have to define the responses. Thereafter, I have to define the critical quality attributes or the CQAs. Okay, once I've defined the CQAs, then I would be going for what is known as the risk assessment. Why I have to go for the risk assessment? So that I can identify the high risk variables. To identify the high risk variables, there are two techniques that I could follow. One technique is by using the Ichikawa diagram, that is the fishbone diagram, or I can go for an FMEA model. Then thereafter, I would be doing screening designs, optimization designs, data analysis, and then also identifying the design space. As I told you earlier, that would be my strategy as far as the design of experiment is concerned. So this is basically what it is, the stage of very important stage of formulation development. In the first go itself, you should have a formulation strategy, you should know the steps that you should be following, and finally you should see to it that you follow appropriate design of experiments. Okay, so let's see what this researcher has done. So first step he did is he analyzed the reference listed drug product. So reference listed drug product he analyzed by searching the reference listed drug on, say for example, on www.fda.gov, that is your FDA site, where you can also have it on the Orange Book, where you can get the RLD product. So he saw the RLD product, he gave its description. Okay, it is an unscented, metered dose, manual pump spray formulation contain a solution of lunisolide. So this already existing. Okay, then the batch number, its expiry date, the strength of that formulation, the RLD formulation, the assay of that formulation, and what was the percent label claim for that formulation, the viscosity of that formulation, RLD formulation, then D50% droplet size distribution of that formulation, all that he has noted down. This is going to help him to actually jot down what is known as the QTPP. So he has done that. Then he has also checked the composition of the flunisolide nasal spray that is already available in the market. So he found out that the composition contained the flunisolide, it contains the various other ingredients that make up the formulation: propylene glycol, polyethylene glycol, butylated hydroxyanisole, disodium EDTA, citric acid, sodium citrate, benz, benzalkonium chloride, then purified water. And then he saw and he visualized what could be actually the functions. What are the specifications for these components? These specification also he got it from the USP or USP National Formulary NF, and he has jotted that down accordingly. Remember, these are the initial stages. And now, after having a complete analysis of the RLD product, he has prepared what is known as the quality target product profile for the flunisolide nasal spray. So you can here you can see the QTPP elements that he has used: dosage form, then route of administration, strength, bioequivalence. Okay, so you can see is listed out all these QTPP parameters. Why he has done that? Because from this he wants to list out the most important responses on which his formulation would be actually focusing on. The most important responses are nothing but the CQS, that is the critical quality attributes. So here from the QTPP, he has identified those responses which are really very important, and that is what is known as the CQS. So, from the QTPP, he has listed out the various parameters here: SAN strength, delivery dose uniformity, then impurities and degradation products, droplet size distribution, spray pattern, microbial limits, leachables, viscosity. And then he has given some justification as to why these would be important and how these are going to affect the formulations. Out of all these CQAs that he listed, he identified some CQAs which are going to really have an influence on the product, and these are which are really very essential, and he should be focusing on if he wants to prepare a similar formulation. Remember, what he's trying to do is he's trying to file an ANDA based on what? Based on the RLD which is already available in the market and whose data is already available, and he can actually analyze the data. So he analyzed the data. After analyzing the data, he prepared the QTPP, and from the QTPP he's identified the CQS. And now what he has done is he's tried to see what are those factors, that is those independent variables which are going to have an influence on the CQS. So he identified two very important CQS. One is the droplet size distribution and the other is the viscosity. And then he has jot down all those factors, all those independent variables that could have an influence on these two major properties. that is the viscosity and the droplet size. So you can see he's jotted down all these variables that could have an effect on these two. Okay, now see, there are so many variables. He has to screen out these variables and identify those active variables only which are going to have an influence on the response. Okay, so for that he has used what is known as the FMEA model. तो दो मॉडल्स उसने यूज किया, ये तो इचिकावा डायग्राम था, दैट इज फिश बोन डायग्राम. फिश बोन डायग्राम से उसने क्या फाइंड आउट किया, उसने ये फाइंड आउट किया कि कौन से ऐसे फैक्टर्स है, ऐसे वेरिएबल्स है जो कि ये दो रिस्पॉन्सेज जो कि सीक्यूएज है, मेरे बहुत इंपॉर्टेंट सीक्यूएज है जो मुझे क्यूटीपीपी से पता चला, जिसके बारे में मुझे आगे स्टडी करना जरूरी है. ठीक है, इस पे उनका इन्फ्लुएंस, कौन से ऐसे फैक्टर्स का इन्फ्लुएंस रहेगा, उसने वो आइडेंटिफाई किया. मतलब वो पूरा जॉट डाउन किया और आइडेंटिफाई करने की कोशिश किया, और आइडेंटिफिकेशन के लिए ही हैज यूज्ड फेलियर मोड एंड इफेक्ट एनालिसिस. सो दिस is known as risk assessment. Risk assessment means what? Means eliminating those which are not going to have much of an impact on the CQAs. Which are the CQAs? Droplet size, and the second sequence that he has identified is the viscosity. So which are not going to have. So he has done what is known as the FMEA model. The FMEA model actually uses what is known as the risk priority numbers. Now, how to identify this? Again, I told you when you start in design of experiment, you have to rely on two very important points, and one is experience and the other is expertise. Okay. So out of experience, expertise, and out of the data which is already available in the literature, we can actually run what is known as the RPN or the risk priority numbers for the various factors and identify the ones which are going to really have an influence on our responses, on those two very important responses that have been identified. Now, obviously, he identified some of these variables. So he identified that ठीक propylene glycol, then polyethylene glycol, disodium EDTA, benzalkonium chloride. These were some of the formulation components जो उसको मिला RLD से. So these are some of the formulation components which would be having very high impact, or they are high risk formulation components. Similarly, he identified some process variables, mixing time, mixing speeds. These are some process variables which are going to have a high impact on the CQAs. And similarly, he also identifies some device variables. Remember, it's a nasal spray. So it's a nasal spray. There will always be a device that would be involved. Remember, it's a meter device. RLD में लिखा हुआ था कि meter device है, तो it's going to be a meter device. So there are some factors as far as the device variables are also concerned, which is going to have an impact. So these device variables he identified as orifice diameter and delivery volume. तो अब देखिए कितने फैक्टर्स उसने आइडेंटिफाई किया. जो प्रोडक्ट वेरिएबल्स है या फॉर्मुलेशन वेरिएबल्स है उसने आइडेंटिफाई किया 1 2 3 4 4, and then process variables he identified, so 4 5 6, and you have your device variables 7 8. So 8 variables or 8 factors he has already identified. Out of these 8 factors he has to do some screening so that he can identify the ones which are most active. Okay, तो उसको screening करना जरूरी है. So what he did is, in the next step he went for doing the screening. Okay, so he identified two levels, high and low levels, for his screening. So these are quantitative levels. So we have understood quantitative levels. So he has identified two quantitative levels, high and low levels, for each and every variable. Formulation variables, for them quantitative high and low levels. Similarly, process variables, two, for them the quantitative high and low levels as far as the mixing time is concerned and mixing speed is concerned. Similarly, the device variables, again he has identified two levels, high and low levels, again depending on the orifice diameter, two levels, and the delivery volume, two levels. Okay, so he has identified two levels of delivery volumes in terms of microliters, and similarly has identified the orifice diameter in terms of millimeters. So this is all what he has identified now, and now he's going to run this design of experiment. So which design of experiment he should take? So he can't go for a full factorial design, obviously, because there are 8 variables at 2 levels. So you can see the number of experiments that he has to perform, 8 into 8. So rather than performing 64 experiments, what he has thought of is thought of going for a fractional factorial design. So the fractional factorial design that he has used is a Blackett-Berman design, wherein you can see the runs that he's operating is a only 12 runs. Remember, Blackett-Berman design is a design which is based on multiples of 4. So he's operating 12 runs for, say, for example, his 8 factors, and he's trying to see the response of these 12 runs on these two important parameters, that is the viscosity as well as the droplet size, which are the actual CQAs. Okay, so he has varied the critical material attributes. These are the materials, and also some of the process parameters he has varied. He's also varied the device parameters, and then he has checked out the changes in all this, the interactions of all this on the final responses, that is y1 and y2. Okay, so you can see here there are 12 runs. Now, out of these 12 runs, some of the runs are repeat runs that he has put in place so that he could actually verify and see whether the outcomes that he is getting are similar outcomes for repeat runs. So that would validate his process, or what you say, it's experimental design. Okay, so for that, these are basically the natural design that or the experimental plan that is given. You can also have a coded experimental plan, that is, rather than using the actual values, you can just put -1 +1 here, and you could have the coded experimental design. Okay, so this was the screening design. These are his results. And from his results, he can then identify the ones which are actually going to have a high impact. So that is done by putting in place what is known as the Pareto analysis. So in the Pareto analysis, we can see which of the ones are most significantly having an influence on the response. So which of these are going to have the significant response, which of these 8 variables are going to have the significant response on, say, the viscosity, which of the ones are going to have a significant effect on the response, say, for example, the droplet size. So we could then now identify not more than 2 factors which would actually having a significant effect on the CQS. And then what I could go for the actual optimization technique. And for the actual optimization technique, what he has done is he's used what is known as the box Bacon optimization design of experiments. Why he's gone for box Bacon? Because what he has done is he's identified 3 rather than 2. If there were only 2, then I would have gone for, say, for example, a 3 by 2 full factorial design where I would be having 9 runs. So why? Because here he is also trying to understand the device parameters. It's not just the formulation parameters and the process parameters, is also trying to identify the device parameters. So the most important device parameter that is thought about is the delivery volume in microliters, because this delivery volume is actually have an effect on the efficacy of the formulation. So what we basically are focusing on, we are focusing on those CQAs which are going to have an effect on the efficiency of that particular formulation in terms of its efficacy, in terms of its safety, in terms of its potency, in terms of its identity. So these are some of the pillars on which the regulator focuses on. Okay, so similar things we focus on when we are identifying the most important CQAs. So CQAs which will have an effect on the efficacy, CQAs which are going to have an effect on the safety, CQAs which are going to have an effect, efficacy means therapeutic efficacy, are going to have an effect on the purity. So these are some of the things that we actually focus on. Anyway, so he has gone for what is known as the box Bacon design. In the box Bacon design, what he has done is he has used 3 parameters or 3 factors over here. Those 3 factors are x1, x2, x3. That is the percent of polyethylene glycol, then propylene glycol, then these are the formulation factors, and also he has used what is known as the device factor, that is the delivery volume. And then he has seen how these are going to have the final effect on viscosity as well as the droplet size, which are the two most important CQAs he had identified in the beginning itself. Okay, so by using the box Bacon design, he has finally come up with these results, and these are the results in terms of the coefficients. And he has found out that, well, the this is the kind of influence the polyethylene glycol and propylene glycol, as well as the device parameter, that was the delivery volume, is going to have on viscosity as well as on droplet size. This is the response surface plot that he got for the formulation parameters on viscosity, and similarly he got a design surface plot of the formulation factors on droplet size. And here you can see that this is the design surface plot that he's got as far as the influence of propylene glycol and delivery volume on viscosity, propylene glycol and delivery volume on droplet size. Okay, by using all these results, he has prepared the relationship, that is the multiple regression has been done, and a relationship has been set between y, that is your response, y1 being your viscosity, y2 being your droplet size, and the various responses. And thereafter he has prepared the contour plots for y1 y2 responses in terms of variation in X1 and X2. These are the formulation variables, propylene glycol and polyethylene glycol, and similarly propylene glycol and the delivery volume. And he has confirmed the design space. So this is the design space. The constraints have been laid down, and he has confirmed the design space. And finally, you could say that he has optimized his formulation. And now this data can be submitted to the regulator along with the other biodata that is done for the batch that is prepared using these uh, quantities of propylene glycol, polyethylene glycol, and using the device with the desired diameter as well as the desired uh, volume, delivery volume. So this is how the optimization process has been done. So that's all I wanted to explain to you with regard to use of design of experiments for optimization. There are many techniques that are available for optimization. This is a particular kind of technique that you could use for optimization, which will give some understanding to the regulator with regard to the scientific basis on which the optimization. So thank you so much. If there are any questions, I'll be happy to answer. Thank you.
Thank you, sir. As the session was very informative and looking into the chat box, our participant has benefited by the guidance they have got from you. Thank you, sir. Thank you very much.
Thank you.
While the presentation is going on, the participants were asking questions regarding the today's topic. So we would like to pick up some questions from them. So shall I start the question answer session, sir?
Please, please.
Okay, the first question is, can you please share about the role of QTTP in QBD?
QTPP in QBD. Yeah, so
Yes, sir.
quality target product profile, as I told you, this is obtained from the RLD, that is the reference listed drug. Okay, and this is the basis of QBD, quality by design. So if I want to design something, so if I want to design a mini Taj, and already there is a Taj Mahal. So already you know that the kind of materials that were used for preparing the Taj Mahal. So those were the critical material attributes. The kind of structure that was finally formed and the kind of impact that that structure gave was your critical quality attribute of Taj, the beauty of Taj. So if I wanted to prepare something like that, a mini Taj, say in Aurangabad, so that mini Taj would have been based on the QTPP that was obtained from Taj Mahal. That is just giving you an idea how QTPP can also be used in architecture. So similarly here, when there is already an RLD product available in the market and I'm going to submit an ANDA, then what I do is I use the quality target product profile of the RLD to prepare my CQA. Okay. And thus, it will help me to design my own product. Okay, by building in quality into that particular product. Not just like that, not by testing the quality later, but by building the quality via design. Because I already know the RLD and I already know the critical target product profile of that particular RLD. So it becomes very easy for me to build a similar kind of a product. Okay, so that is one point. Now, the second question could be from your side that fine, what if there is no RLD? What if there is a completely new product? Can there be a QTPP? Okay. Can there be a QT? Can I build up a quality target product profile? Yes. What is the kind of innovation you want to do? Okay. And this innovation would be based on which kind of outcomes that you're seeking. So your outcomes basically would be your QTPP now. So what you are imagining, the kind of outcomes you're wanting to seek, those outcomes would be your QTPP. So according to that QTPP, you have to identify those important, very important outcomes, which will be your CQS. Then what is the materials in your formulation which will be having an effect on your CQS will be your CMAs. Okay. So it depends. If there is already a formulation which is available and you're going for just preparing what is known as a design space, for submitting your ANDA, then it becomes very simple. You just take the RLD, prepare the QTPP, and operate QBD. If it's an innovative product, then you have to prepare your own QTPP depending the outcomes you want from that particular innovation. Yes.
Okay, sir. Now the second question, sir, is there any limitations of QBD?
Limitations of QBD. See,
Yes.
QBD is quality by design. So, depending on the kind of the process or product that you are trying to design, okay, there could be limitations. As far as QBD as such is concerned, it is just uh, some standard operating procedures that have been laid down wherein you could build in quality into a product. Okay. But the kind of tools that you would be using to solve those limitation per se, your product or your process is important. So, as such, as an operational process, a standard operational process that is being given under Q8 guidelines or Q9 or Q10 guidelines, there are no limitations, so to say. But yeah, when you are formulating your product or when you are trying to prepare your process, the tools that you would be using, there could be some limitations there, and you would have to overcome those limitations by using. So, one method of overcoming limitations and challenges in process parameters is PAT. So, that is using process analytical technologies. So, by using various process analytical technologies and new technologies which are based on Raman spectroscopy or NIR, that is near infrared spectroscopy, you can actually overcome those challenges, okay, for fixing your process parameters. Okay, so per se QBT as such, you can't identify limitations, but yeah, there's a lot of advantage over the conventional techniques. So here in QBD, you know that we are defining what is a design space. There is actually a more scientific approach, or more, it is based on a more scientific method. Okay, and there a lot of understanding, not only from the innovator side, but you could make the regulator also understand your process better. So it has got greater advantages over the conventional techniques. As such, you wouldn't say there is any limitation to this particular technique. But yes, when you are using the technique for various formulations or processes, there could be some issues which you'll have to face, and you'll have to overcome these challenges using newer technologies. Now, one important thing I mentioned is using of AI, artificial intelligence, or using ANN. So these are some better techniques for optimization, and understanding these techniques is again a challenge. Making these techniques operational or operative is again a challenge. Validating the computers, the computer applications, validating that those apps again is a challenge. So these are some challenges which needs to be overcome.
Sir, what are the importance of QBD in quality assurance?
QBD in quality assurance. Quality
Yes,
by design is basically to, you know, assure that your final product or even an analytical method is the best. Okay. So, utility in quality assurance, even in total quality assurance for a particular process and a particular product is enormous, because here you are not just building in quality and testing it later, but you are seeing to it that the quality is assured before you actually go for that particular experiment, go for actually the particular process, or go for actually preparing that particular product. So what you are doing is, uh, pre the process or pre product experimentation, you are preparing a design based on the known scientific facts, known data that is available. So it makes your product more you know having the quality much more assured than using a conventional technique, where you are using quality control tests to actually see whether you are getting the generally the kind of quality that you design the process or product.
yes, sir. Now, last question, sir. What is the benefits of PAT throughout the pharmaceutical manufacturing industry? Process analytical technology.
Yeah. So process analytical technology is something that is growing day by day, and basically, as I told you, for CPP, that is for identifying the critical process parameters and also studying these critical process parameters, PAT is a very important tool. Whether you're using DOE or whether you are using PAT, these are tools as far as QBD is concerned. Which tool you would be going for, which tool you would be using is at your liberty. The regulator is not imposing on you that you use DOE only or you use PAT, process analytical technology. But these are some of the tools which are available with you. And there are many other tools which soon will be available s- from the kind of advances that we are doing in computing, basically as far as artificial intelligence, robotics, and so on and so forth is concerned. So yes, it is becoming more and more important. Pat, see, I could have online monitoring being done for the various processes that is being uh, conducted without being on site. I could be doing the monitoring sitting, in some other country for the processes that is happening, say, for example, in an unit in India. You know, I could actually supervise these processing. This is what online technology has brought about. I could actually see what is the moisture content in a particular machine by placing appropriate probes in that particular machine, which will actually sense be having those sensors which would identify the moisture changes that are taking place, as say for example the rapid granulator mixture is functioning. So those sensors can be placed. I could have transducers placed which could actually measure the pressure changes that are taking place. I could use NIR technology, which will make me understand the kind of active ingredients which are actually being transported, okay, into, say, for example, the processing area, or those which are coming into the quarantine area. So, without actually opening the container, okay, by just scanning using the NIR technology or using Raman, I could do a lot. So PAT is going to have a great impact in making our processes, more effective in pharmaceutical companies, pharmaceutical industries. And this kind of data is going to really be useful for getting our approvals through as far as the regulators are concerned.
Yes, sir. Thank you, sir. It looks like we have covered all the questions, so I guess there is no any more question. So, thank you all the participants for your active responses, and thank you, sir, for resolving all the queries of participants. Now, I would like to present certificate of appreciation to Dr. Degan, sir.
Thank you so
Please, sir,
much.
accept our certificate.
Thank you.
Thank
God
you,
bless
sir.
you all.
Now,
Thank you
I
so much.
request Miss Ragini ma'am to present vote of thanks. Am I audible, sir?
Yes, 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 yes.
Thank you, sir. A very good afternoon to all of you. I am here to present a vote of thanks as the gratitude is the key to share the happy feelings. On the behalf of Adarsh Shikshan Prasarak Mandal, KT Patil College of Pharmacy, and on the behalf of all the participants, I am Ragini Rajmane, very much glad to present vote of thanks for this one-day seminar on applications of KBD in pre-formulation study. First of all, with lots of gratitude and respects, I would like to thank a knowledgeable and eminent personality and the speaker of today's seminar, respected Dr. M.S. Degan sir, for sparing their valuable time and knowledge with all of us. Thank you, sir. I must say the session was very informative and it will definitely helpful for upgrading our knowledge pertaining to the said subject. Thank you, sir. Sir, we will be always grateful for your kind support and cooperation for success of this seminar. Thank you, sir. Thank you so much, sir.
Thank you. Thank you so much. Have
I
a good day.
also would like to mention, sir. I also would like to mention my special thanks to principal and the convener of this seminar, respected Dr. Amul Joshi, sir, for arranging such an informative session for all of us. Thank you, sir. With gratitude, I wish my humble thanks to our supporting management, a backbone of our institute, President Sri Sudhir Patil sir and the administrative officer Aditya Patil sir and all the body members for their endless efforts. Thank you, one and all. I also would like to thank coordinator of today's seminar, Dr. Amit Kaji sir and Mr. Nadeem Khan sir for their endless support. Thank you, sir. I also would like to thank Ms. Rubia Kazi Madam and Dr. Sarfraz Tambul sir for arranging such a nice seminar without any disturbance. Thank you, sir. Thank you, ma'am. I also would like to thank backbone of our institute, Vice Principal Ms. Geeta Sapta Madam and IPSC Coordinator Sudhir Pange sir and all the faculty members. Thank you, sir. Thank you, one and all. Last but not a least, I would like to mention my special thanks and heartfelt thanks to all the enthusiastic participants for their all-willing response for this one-day seminar. Without any support, it would be impossible to conduct this seminar. Thank you, one and all.
Thank you, ma'am. Bye bye.
There are some instructions for the participants. The feedback link for the today's seminar was already shared in the chat box of WhatsApp group and the YouTube. So do feel the feedback positively. Link will be remains active only for 30 minutes. Thereafter, the link will be closed. So be fast. And as the number of participants are near about 100 or near about 500, so you will may get the certificate very late. We will try to issue the e-certificates within 15 days. So do have a patience. Once again, thank you one and all. So now, with the due respects, we would like to conclude our session.